In this video, we're going to do an example of coming up with a design of a control system that meets certain specifications, performance specs, where the performance specs are in terms of meeting measures of performance for a step response. And that's what we just talked about in previous videos. Oops. So here's the problem. We're given this block diagram with these two parameters in it, two design parameters, K and K sub, I think that's a T, K sub T. Yes. And to meet two different specs. One is maximum overshoot of 4.3% and a rise time, that 10 to 90% rise time of 0.2 seconds. And kind of give you a spoiler alert, this is a nicely spec problem because it gives you exactly two specs, which are exactly what you need to come up with those two parameters. And they don't conflict. You can meet these specs. You can be given a problem where you can't meet the specs. You can also be given an overspec'd case where you might be given too many specifications. And anyway, so let's go through this. The first thing we're going to have to do is come up with a transfer function. And let's hope it's a second order system, or else we don't know how to deal with it yet. Well, I'll go through kind of a review of Mason's rule to get there. Let's look at this. There's only one forward path, straight down the line here, because all the other paths are feedbacks. So there's one forward path, and I see two loops. This loop here, this bigger loop here, they both touch the forward path. That's good news. That means those little minor determinants are just one. So the numerator of our transfer function is just going to be the forward path product, or the forward path gain, which is just this K times this G sub P times this 1/20S. And on the denominator, both loops, these two loops touch each other. So I don't have any of those pairs or triplets. So it's just going to be 1 minus the two loop gains. The loop gain of this guy will be this G sub P times this K sub T. Loop to the outer guy is going to be K times G sub P times 1/20S. Everything I just said goes right here. The rest of these steps are algebra, which gets me to this. And lo and behold, this is a prototype second order system. Numerator matches this term, so it's a prototype system. Its final value is going to be 1. And we can relate the K's to natural frequency and damping ratio. The natural frequency is the square root of this. And this whole mess here is 2 zeta omega n. So we can match our second order prototype parameters to the K's that are needed. So now we need to translate the specs into zetas and omega n's. We're given a peak overshoot spec. We had this formula from our formula sheet. Remember, we're using a formula sheet. We go way back. Here's our formula sheet. Here's the one that relates peak overshoot to damping ratio. It says plug it in. I think this is approximately or exactly 1 over the square root of 2. Approximately 0.707. And the other spec was a rise time spec. Said this. Now we have the zeta, we can plug that in there. That had to equal 0.2 seconds, so we can solve for omega sub n. This omega sub n is 113. If I'd used that other simpler formula, I think I would have got exactly 9 here, 81 here. I didn't do the rest of the design. If I had done that, anyway, I'd use this formula, which is supposedly the more accurate formula um, from the formula sheet. Go back to the formula sheet. There was 2 formulas for rise time. This one and what we consider a less accurate one, but we use this guy when we want to know where the pole locations are. But when translating specs, parameters, we'll use this one on the left. A little bit more accurate or complicated. So now we have everything we need. We have omega sub n and zeta, and we can translate them back into the Ks. So we have our 2 Ks. We've solved the problem, at least by the numbers. Here's where you get into the more bigger design process. Let's see how that works. Here we got to use MATLAB. I'm not going to teach you MATLAB. If you do control systems, you're probably going to have some MATLAB toolbox for controls, or even if you generated your own programs. This is what that response would look like. And when we calculate exactly, the peak overshoot was 4.2, 4.3 or less. Rise time was right on, 20 seconds. So this is pretty close. If you didn't like this, say you are not allowed to exceed the spec by 1 iota, you might use a little bit of trial and error, not moving too far from the parameters you already had. If I did some of that trial and error, I came up with slightly different Ks, and now I'm just slightly under the 4 point. I'm still beating the rise time spec, but I'm under spec barely, or the overshoot. 4.7 and 4.5. So we didn't deviate too much from these numbers. So that's a sort of end-to-end case of using all those performance measures and formulas to meet specs. Working with a prototype second-order system.